Yo, 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 this is Eduam, aka Sazen Mixia, aka Mason and Cesar. Coming at you right now, gonna answer some orange questions. So,
Shall I beatbox for you?
for number A,
Letter A. Letter A.
letter A, we have a second order reaction. Second order. We know this because when you plot the graph concentration over time, it is curved. When you plot ln of the concentration over time, it's also curved. When you plot the inverse of concentration over time, you get a linear graph. This indicates that it's a second order reaction. Now, for letter B, Cesar will be going through that question with you.
Alright, so when it comes to determining what the rate law for the reaction is, we need to keep in mind a formula that is K times the concentration of the reactant to a certain exponent. In this case, the reactant that we are working with is C4H6. So the rate law for the reaction is going to be K C4H6. Does this go further?
Nope.
Alright, sorry. I'm going to have to erase this really quickly. But, yeah. Sorry, guys. I think we need to restart this recording.
Okay, that's fine. How about
I thought I was gonna go through I thought this was
how about we'll do
have you seen the Khan Academy videos?
Yeah.
Where and they had unlimited
yeah.
space and they keep moving. I thought that's what this was.
Oh, those mother duckers.
And we wouldn't be able to do C or D.
How about we just do A?
Okay, we do it.
Hey, coming right at you. It's Cesar and Mason, aka our alias today is Eduam, combining our middle name. So, going on for the orange question number 1. Question is, the unsaturated hydrocarbon butadiene, am I pronouncing that right? Dimerizes to blah. Data collected in Kinetics studies of this reaction were plotted in multiple ways. The graph of C4H6 versus time was curved. The graph of ln C4H6 versus time was also curved. But the inverse of C4H6 was linear. So, in answering question A, what is the order of this reaction?
Too much space. I know.
Because the graph of C4H6 versus time is curved, and the natural log of C4H6 over time is also curved, and yet the inverse is linear, we know that this is a second order reaction. It's as simple as that, ladies and gentlemen. Hand off to Cesar for the second question.
Hello. Well, the second question asks, what is the rate law for the reaction? Now, we know that the formula for rate law is K times the reactant to the exponent M. So in this case, the reactant we're looking at is the hydrocarbon butadiene. So the rate law for the reaction is going to be K, which is the rate constant, times the reactant's concentration. So in this case, the reactant is C4H6. And because it is a second order reaction, it is going to be squared. And that's all. Go Colonels.
Alright, yo, what's up? Going on to question C. How could the rate constant for the reaction be determined? Well, all you need to do for a second order reaction is take the slope of the inverse of the chemical you're looking at, in this case C4H6, versus time. So, draw a little graph over here. Over C4H6. Concentration It's going to be linear and positive. And then over time, you're going to take the slope, and that'll give you the K constant. Now for final question, D.
So it's back to me. The final question asks, how many half-lives will it take for the compound, the hydrocarbon butadiene, to decrease to 3.1% of its original concentration? Well, we know that at the start of this problem, you have 100% concentration. And so basically the process for this is to divide the original concentration, which is 100%, by 2 until you get to the number closest to 3.1. So you start with 100, you divide by 2, that gives you 50, divide again by 2, 25, 12.5, 6.25, and then that gives you, on the fifth division, 3.125, which is the closest value to 3.1%. So basically, you need to go through 5 half-lives in order to get to the concentration or to decrease to 3.1% of its original concentration. That's all for now.
See you later, yo.